Here, we're going to look at a longer free response question that covers a variety of skills and concepts that you've learned in AP Chemistry. Now, because this item is so long, we'll take the questions one part at a time. You can download a mini test here. You can practice, try it yourself, and then you can follow along with this video. All right, let's get started. Part A asks you to indicate the hybridization of the carbon atom in formaldehyde. This is a pretty common task on the AP exam, so you want to be sure to know your basic hybridization schemes. There's an easy trick to identify hybridization. Just look at the atom in question and count the effective electron pairs. Okay? An effective electron pair includes single bonds, double bonds, triple bonds, and lone pairs. Each of these units is an effective electron pair. So, if the atom has 4 effective electron pairs, it adopts an sp3 hybrid orbital scheme. Okay, in the examples right here, the carbon atom in methane would have an sp3 hybridization because of the 4 effective electron pairs. That's the 4 single bonds here. But the oxygen in methanol would also have an sp3 hybridization because it has 4 effective electron pairs, 2 single bonds and 2 lone pairs, also an sp3 hybridization. Now, an atom with 3 effective pairs requires sp2 hybridization. So that's like the carbon here in formic acid, right? We have 2 single bonds and 1 double bond. Also, the oxygen here, 1 double bond, 2 lone pairs. Again, in both cases, 3 effective pairs, so sp2 hybridization. Finally, an atom with 2 effective electron pairs uses sp hybridization. These atoms usually have a triple bond. None of the molecules here meet this criteria, but it's still something to be sure you know for the AP exam. Okay, so moving on to the question here, look at our carbon atom in formaldehyde. It has 2 single bonds and 1 double bond. That's 3 effective electron pairs. So sp2 is going to be the hybridization of our carbon. Okay, part B. Still, we're kind of talking about bonding here. In this case, we're indicating the approximate bond angle of the COH bond in, COH bond in methanol. That's this one right here. Okay, since we're only talking about methanol, let's blow it up so we can take a better look at it. Now, this is a bond angle question, so it's helpful to review some common bond angles, which are related to the overall shape of the molecule. Okay, there are 3 main numbers to know here. Okay, linear is 180 degrees, which makes sense. Now, for molecules based on trigonal planar geometry, it's 120 that you want to know. And for tetrahedral geometry, it's 109.5 degrees. You should have these 3 common bond angles memorized. Now, what is the overall geometry of this bond here, or these bonds here? Okay, the oxygen atom in methanol has 4 effective electron pairs, right? These 2 bonds, these 2 lone pairs. So that means it has sp3 hybridization. It has 4 things arranged around this atom. That means that its geometry is tetrahedral. Okay, so this is the number that we're going to be using. This may seem confusing at first, right? Because on paper, it looks linear. But remember, this is a 2D Lewis structure that we're looking at, not a 3D VSEPR diagram. So if we were to pull up a ball and stick model, this carbon-oxygen-hydrogen bond would look like this, right? These models don't show the lone pairs, but we have these 2. One would be here, one would be on the other side of the oxygen. And so this bond angle is going to be 109.5 because these are two of the bonds of a tetrahedral geometry. So 109.5 is our approximate bond angle. Now we're saying approximate here because these lone pairs are a little bit more repulsive than single bonds. If we had 4 single bonds, it would be almost exactly 109.5. These lone pairs are going to push a little bit, make the bond angle a little bit smaller, but you don't have to worry about that. For the AP exam, 109.5 is all they want. Okay, so let's move on. Now, part C here gives a table of boiling points. That's right here, and it asks the boiling points of the 4 compounds. The 4 compounds are shown in the table below. Use the concepts of intermolecular forces to explain why methanol has a higher boiling point than formaldehyde. So now we're looking at boiling points. You see how we're kind of switching through topics but still looking at the same molecules? This kind of scheme is very common for longer free response questions. Okay, as before, we're only going to focus on these 2 relevant molecules. Now, whenever the AP exam shows you molecular structures and asks you to compare boiling points, the question is usually about intermolecular forces of attraction. Here's the main point. In general, the stronger the intermolecular forces of attraction, or IMFs, the more energy it requires to break the bonds. This translates to higher melting points and higher boiling points. Now, the truth is, this table isn't actually needed to answer the question. It's just offering data that shows that methanol boils at a much higher temperature than formaldehyde. But the question already told us that. So we can get rid of the table and we'll use the space to blow up our molecules here. Now, remember, because methanol has a higher boiling point, it's going to have stronger intermolecular forces of attraction. That's what we're looking for here. So we can just put this down here to remind us. Let's examine the intermolecular forces that each of these compounds experiences, okay? They both have the same elements: carbon, oxygen, and hydrogen. Now, oxygen is pretty electronegative compared to carbon and hydrogen, and that electronegativity causes uneven sharing of electrons, and that causes the atoms in these bonds to develop partial charges. We can mark these partial charges with a lowercase delta sign here. So, if we look at polarity, we can see that both molecules are going to be polar. And that means that since they're both polar, they're both going to experience dipole-dipole interactions. That's useful information, but let's look closer. What's the difference between these molecules? Notice this hydrogen over here on the methanol. Okay? It's bonded directly to an oxygen atom. This is a classic setup for hydrogen bond. The AP exam always has a hydrogen bonding question in there somewhere, so be sure to understand what a hydrogen bond is, okay? When a hydrogen is bonded to a very electronegative partner, like oxygen, nitrogen, or fluorine, it experiences an attraction for nearby electron pairs. And we call this a hydrogen bond. It's the most powerful force of intermolecular attraction. And since methanol has electron pairs on the oxygen, methanol molecules form hydrogen bonds with each other. This hydrogen would hydrogen bond to the lone pairs of oxygen on another methanol molecule, right? These are powerful bonds, and they help to keep methanol liquid at room temperature. Now, over here on the formaldehyde molecule, the hydrogens are just bonded to carbon. Carbon has a relatively low electronegativity, so the hydrogens bonded to carbon aren't going to form hydrogen bonds. Now, in summary, both molecules experience dipole-dipole attractions, but the methanol also experiences hydrogen bonding. So, methanol has stronger forces of intermolecular attraction and therefore a higher boiling point. You could explain this in a number of ways. Your answer could look something like this, okay? Methanol has a higher boiling point than formaldehyde because the hydrogen attached to methanol's electronegative oxygen is prone to hydrogen bonding with the electron pairs on adjacent methanol molecules. This is a very strong intermolecular attraction requiring much energy to break. By contrast, formaldehyde only has a carbon-oxygen bond, which can only participate in dipole-dipole attractions, which are weaker than hydrogen bonds. Again, as long as you touch on the main theme here, hydrogen bonding, strength of intermolecular forces, you'll earn the point. Part D, another question about intermolecular forces. A student argues that methane molecules experience no intermolecular forces. Explain why the student is or is not correct. Well, let's think through this. Methane is made from 4 hydrogen atoms connected to a carbon atom. Carbon and hydrogen have relatively similar electronegativities, so that means that these are non-polar bonds. The electrons are shared more or less equally. So methane overall is a nonpolar molecule. There aren't going to be any dipole-dipole interactions. And since carbon has a pretty low electronegativity, the hydrogens in methane aren't going to be doing any hydrogen bonding either. So at first, you might be tempted, like our imaginary student here, to say that methane does not experience any intermolecular forces. But think that through. If methane molecules experienced no forces of attraction whatsoever, how could methane ever turn into a liquid? Even noble gases can be liquefied at cold enough temperatures. So, all particles have to experience some kind of intermolecular forces, right? They do. We call these London dispersion forces. They arise from the random motions of electrons. At any given instant, the random movement of electrons can create temporary dipoles, little zones where you have a partial positive and a partial negative charge. And those create little flickers of attraction. London dispersion forces are the weakest of the intermolecular forces, and they only really kick in at low temperatures. But you should still be familiar with them for the AP exam. All particles experience London dispersion forces, even noble gases. Otherwise, we could never liquefy nonpolar substances. So, your answer should read something like this. The student is incorrect. All particles experience London dispersion forces which arise from the random motions of electrons. Okay, with part E, we switch to another topic. Now we're going to get into some math. Here we have the equation for the combustion of methanol with oxygen. And the question asks you to calculate the standard enthalpy change for the reaction using this data from an enthalpies of formation table. Now, the math for this problem isn't too difficult, but it takes up a lot of space. So we're going to clear some of this out, just keep the stuff we need. All right, that's our table, our formula, and our instructions. This is an enthalpy of reaction problem. So to solve for the change in enthalpy, we need to use this equation. The delta H of the reaction equals the sum, that's this sigma sign, the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation for the reactants. Fortunately, this is one of the equations that the AP exam will give you. Just remember, this degree sign means these values were calculated under standard conditions. Now, it's easy to get lost in these kind of sigma problems, so be sure to take your time, show all your calculations. Here, we do the sum of the products minus the sum for the reactants. Let's start with the products, okay? We have CO times 2. Don't forget the stoichiometry of the reaction. You want to bring the coefficient down here. And then we have H2O times 4. Now we'll add in the reactants again, pulling in the coefficient from the balanced chemical equation, 2 with methanol and 3 times oxygen. Okay, and now we can fill in these values using our table here of standard enthalpies. Here you want to be really careful with your signs, negative and positive. We're skipping the units because they're incredibly messy. We'll discuss the final unit at the end of the problem. Okay, so here we have 2 times the enthalpy for carbon dioxide, which is negative 393.5. Then we have 4 times the enthalpy for water, 2 times the enthalpy for methanol, and finally 3 times 0.0, which is the enthalpy of oxygen. It's useful to remember that the enthalpy of any element in its natural state is 0. So that makes this equation a little easier on the math. We sum up these, and we get negative this minus negative that. Again, be careful with the signs, okay? Losing track of these negatives is a very common mistake that students make when they're solving these problems, okay? You do this math correctly by accounting for the proper signs, and you get negative 1,528.2. Now, what about the unit here? Normally, the answer would be in kilojoules, and that's what you'd see in most textbooks. This is the energy released by the balanced chemical reaction. 2 moles of methanol combusting with 3 moles of oxygen. Now, some textbooks will clarify this by adding a per reaction, like this. That's also fine. But here's the thing. The AP chemistry exam uses a weird unit that's much less common, and that's kilojoules per mole sub-reaction. You may see this unit on a practice test or in an AP exam prep book, so we'll include it here. But don't worry about this too much. The AP graders are more focused on the correct value, negative 1,528.2 kilojoules. That means the reaction is exothermic. It's releasing heat, which makes sense because this is a combustion reaction. Okay, the final question is related to the previous one. It gives you the density and the molar mass of methanol and asks, how much heat will be released when a 150.0 milliliter sample of methanol is combusted with an excess of oxygen? To answer this question, we'll need the value of delta H, the enthalpy change we calculated in part E. That's this right here. And remember, this value is for the overall balanced reaction. So to use this, we'll need to figure out how many moles of methanol actually react. Well, if the problem had just given us grams of methanol, this would have been really easy. We just take the grams of methanol and use that to calculate moles, right? But the problem gives us the density and the volume of the methanol, okay? Fortunately, we can use the density and the volume to calculate mass. Then we'll use our molar mass to solve the problem. Okay, so density equals mass divided by volume. We can rearrange it. So we get mass equals density times volume. We have the 2 values that we need for that, right? We have the density, which was given, and the volume, which is given. Milliliters here are going to cancel out, so we don't have to worry about any conversions, and we get a mass of 119 grams, rounded to 3 significant figures. Okay, so now we know the mass of methanol. We rearrange this equation. Moles equals grams divided by molar mass. plug this in for the mass of methanol. The problem, very convenient, gives us the molar mass. We can put that in right there. This divided by this gives you 3.71 moles. That's how much methanol we actually have, 3.71 moles. Now that we've calculated moles, we can answer the question. Let's get rid of these calculations here. We don't need them anymore. We'll bring our moles up here. Okay. And now, to solve the problem, we'll use dimensional analysis. We're going to build a chain of conversion factors that leads us to the correct answer. There are other ways you could solve this, but most teachers and textbooks would use dimensional analysis. Okay, so we start with 3.71 moles of methanol. That's our known. We just calculated. We could have started with the delta H, but this way I think is more direct. Now, we need to know how many moles of methanol are in the balanced equation. Well, here's our equation. There's 2 moles of methanol in the reaction, and we can turn that into a conversion factor, 1 reaction per every 2 moles of methanol, or the other way around, however you want to say it. Okay? That means that moles of methanol cancels out. Now, we need 1 more conversion factor here, and that is our enthalpy per reaction. Okay? Now, reactions cancel out, and we do this math, insert it into your calculator, and round it to 3 significant figures. It's going to be negative 2,830 kilojoules. Now, before we finish up, notice how many different topics the free response question covered, right? We did Lewis structures, hybridization, bond angles, intermolecular attraction, boiling points, enthalpy of formation, combustion reactions, a little stoichiometry. And notice that some parts depend on others and some parts were independent. So you should always work carefully, but don't get discouraged. Try every part of the question and show all your work. That's a way that you're going to get partial credit. Okay? So, as you prepare for the AP Chemistry exam, I wish you the best of luck. Take a look at my website. I hope the resources there are helpful for you, and I hope you ace it on test day.